All right, so you're ready for another deep dive. We're going deep today. But
Yeah.
first, before we get into it, I want to remind you about all the other amazing stuff happening over at the All Sorts podcast. We've got a really beautiful YouTube channel. You should check it out. Videos, yeah, nice audio, visuals. Give us a like, share with your friends, if they're into learning and stuff. And subscribe so you never miss an episode or, a deep dive, I should say.
Deep dive, exactly.
We also have tons of past episodes, so, if you're new here, go back and check out some of those, some really good stuff back there. And be sure to follow us on all the socials, X, Instagram, Threads. That's where the conversation keeps going. The All Sorts podcast community, it's a great place to be. All sorts of ways to join us and learn some more.
And today we're diving into something really fascinating, I think. The history of MRI, magnetic resonance imaging. This amazing technology that lets us see right through the human body.
Right. And you, the listeners, sent us a ton of great sources for this one. We've got articles from Ezra, Midwestern Career College, PubMed, Science Direct, a little bit of Wikipedia, NSF, Siemens Healthineers. It's quite the mix, really.
Yeah.
So what we're going to try to do today is bring it all together, tell the story of how this really powerful technology came to be.
So to start, I think we need to rewind way back. Before we had the amazing images that we have today, before MRI was used in hospitals and clinics everywhere, scientists were exploring this really fundamental idea. It all starts, really, with how atoms, like the nuclei of atoms, how they act when there's a magnet around.
So going back all the way to the 1930s, I.R. Rabi, a physicist, really brilliant guy, he was the first to figure out how to actually measure the magnetic properties of atoms, of atomic nuclei, I should say. He even used this to study how sodium atoms move around. Really foundational work because it basically revealed this phenomenon of nuclear magnetic resonance, or NMR. And that's the quem idea behind what makes MRI possible. Yeah. And of course, he won the Nobel Prize in Physics for this work in 1944.
Well deserved, I'd say.
Absolutely.
So then, moving into the 1940s, we have two more physicists, Felix Bloch and Edward Purcell. And they were working completely separately on different continents, just doing their own thing. And both of them, they started studying how atoms and molecules, in solids and liquids, they were studying how those things behaved in magnetic fields. Their research really showed that MRI could work, specifically that you could use water, which is, everywhere in the body, to make these images.
Pretty incredible.
Yeah, amazing stuff. And they both won the Nobel Prize in Physics, too. In 1952, they shared it.
Wow. I mean, that's two Nobel Prizes already just for the basic science behind MRI.
Yeah. It really shows, how fundamental these discoveries were.
But, okay, so we've got these amazing physicists figuring out how atoms respond to magnetism. But how do you actually go from that to, creating an image of what's going on inside someone's body? That seems like a huge leap.
Yeah, it is a big jump. And I think one of the things that made it possible was this idea that different tissues in the body, they don't all hold water in the same way. The water molecules in your muscles behave a little differently than the water molecules in your bones, for example.
Oh, interesting.
Yeah, and that was figured out in 1955 by these two Swedish researchers, Gunnar Lindström and Erik Odeblad. They basically theorized that the way water is absorbed and organized in different tissues, it could explain why they give off slightly different NMR signals.
Ah, so it's each type of tissue kind of has its own water signature in a way.
Exactly. That's a really great way to put it. And so, the water itself becomes a natural contrast agent. And this idea really opened up the possibility of actually distinguishing between different types of tissue in an image. And, while all of that was going on, there were a couple of other important things happening in the world of NMR research. So in 1950, Erwin Hahn, he discovered these things called spin echoes and free induction decay. And they're really important signal events. They allowed researchers to get clearer, more detailed measurements in NMR.
Okay.
Yeah. And then in 1952, Herman Carr made the first one-dimensional NMR spectrum, which is basically, a graph that shows all the different magnetic resonance frequencies in a sample. So little by little, the tools for harnessing NMR were getting better and better.
So it seems pretty early on, people started to think, hey, we might actually be able to make images with this, even if the technology wasn't quite there yet.
You're right. And in fact, in 1960, a Soviet scientist named Vladislav Ivanov, he actually applied for a patent for an MRI device.
Wow, in 1960.
Yeah, way back then. His idea was to use gradients in the magnetic field. So basically, varying the strength of the magnetic field across the body to like encode spatial information into the NMR signal. It's like giving every point in the body its own little magnetic address. And it was, way ahead of its time, actually. His initial patent application was rejected, but then much later it was approved in 1984.
So, credit where credit is due.
Exactly. He had this really insightful vision for what MRI could be, even though the technology to actually build it wasn't there yet.
Right. So all of these early discoveries, all of this research, it was all coming together. And then in 1969, Dr. Raymond Damadian, he makes this huge breakthrough.
Yeah, he made this amazing hypothesis, and then he went and proved it with experiments on rats.
Yeah.
He showed that, yes, magnetic resonance can actually tell the difference between cancer cells and normal cells. And the way it did that was by looking at these things called relaxation times.
Relaxation times.
Yeah, so basically when you hit a sample with radio waves in an MRI, the atoms get excited, and then they release energy as they go back to their normal state. And the time it takes for them to do that is the relaxation time. And what Damadian found was that cancer cells had longer relaxation times than normal cells.
That's a game changer.
It was huge. It meant that potentially you could use MRI to detect cancer without having to cut someone open.
Did people believe him right away?
Well, with any big scientific discovery, there's always going to be some skepticism, some healthy debate. And to be fair, the reasons why cancer cells have different relaxation times, it's pretty complex, and it took more research to really understand that.
Sure.
But even so, Damadian's work was this crucial first step.
And he didn't stop there, right?
No, he kept going. Building on his research, he proposed building a whole-body MR scanner in 1969. And then in 1972, he filed the first patent specifically for MRI technology. Got it approved in 1974. And incredibly, he actually went on to build the very first full-body MRI machine. Called it Indomitable, which I love. And that machine is now in the Smithsonian, which is so cool.
That's amazing. So that's where it all started. And then just a few years later, in 1977, Damadian and his team, they create the first ever NMR image of a human being. It's pretty hard to even imagine what that must have been like, to see inside the body in that way for the very first time.
Yeah, and it was just a cross-section of his assistant's chest, but it clearly showed his heart, lungs, vertebrae, muscles. It was revolutionary.
Incredible. But Damadian wasn't the only one working on this, right?
No, absolutely not. Around the same time, you've got this chemist, Paul C. Lauterbur. He's also working on MRI, but he's focusing on different aspects. He's really into how to actually create the images, like how to use magnetic field gradients to build up a two-dimensional picture, and then how to stack those 2D slices to get a 3D view.
That makes sense. So Damadian builds the first machine, gets that first human image, and Lauterbur is figuring out the spatial encoding, the where of the signal.
Exactly. And he came up with this term, zoogmatography, for his technique. It's Greek, means something like to join together what is perceived. So, he's bringing together all these signals from different parts of the body to make one complete picture. He publishes the first NMR image in a scientific journal in 1973. And then a year later, he publishes the first cross-sectional image of a living mouse.
That's amazing. So where does Sir Peter Mansfield fit into all of this?
So Mansfield was a physicist, and he was really focused on making MRI faster and more practical. Early MRI scans, they could take hours. Literally hours to produce one image.
Oh.
It was a big problem. And he managed to get it down to 23 minutes for an image of a finger. The first successful scan of a human body part that really cut down the time significantly. But, his biggest contribution was probably echoplanar imaging, EPI. This technique made it possible to get images in just seconds. So it's fast enough to capture a snapshot in time.
That's incredible.
Yeah. His team even got the first EPI images of a beating rabbit heart. Really fast stuff. And then they moved on to imaging human infant hearts in the early 80s. Pretty remarkable.
It's amazing to think about all these brilliant people, all working in their own labs sort of in parallel, and they're all making these essential contributions to what MRI would eventually become. Makes total sense that Lauterbur and Mansfield shared the Nobel Prize in Physiology or Medicine in 2003 for their work on MRI.
Yeah. Very well deserved.
Okay, so now we have the basic technology, the imaging techniques. What happens next? How does MRI go from a research project to something that doctors are actually using?
Well, Damadian, the guy who built the first full-body scanner, he goes on to found a company called Phonar Corporation in 1978, and they make the first commercially available MRI machine in 1980.
So that's pretty quick. from like the lab to the market.
Yeah, I mean, it just shows you how much potential everyone saw in this technology.
Yeah.
And Phonar, they kept innovating. They introduced the first mobile MRI unit in 1985, which was really important because it meant you could bring MRI to patients who couldn't easily travel to a hospital, like people in intensive care or in emergency situations.
I see.
And Damadian was also involved in developing the first MRI-compatible pacemaker. Because, obviously, you don't want the strong magnetic fields messing with someone's pacemaker.
Huge safety concern.
Exactly. So while all of that was happening in the U.S., over in Germany, you have Siemens, another big company, also working on MRI. And they actually produced the first MRI image in Germany in 1978. But their first image was of a bell pepper.
A bell pepper?
Yeah, a bell pepper. Kind of a funny little footnote in the history of MRI.
That's great.
But, in 1980, Alexander Gasson, who worked at Siemens, he actually volunteered to be scanned. That was a pretty big step.
Very brave of him.
Yeah. And later that year, Siemens did their first full-body scan. So things were really moving quickly. And then, in 1983, Siemens installed their first clinical MRI machine at Hanover Medical School. And in August of that same year, the very first commercial Siemens magnetum system went into operation in St. Louis, Missouri.
So both in the U.S. and in Europe, MRI was going mainstream.
Absolutely.
And around that same time in Scotland, a team led by John Millard at the University of Aberdeen, they had also built a full-body MRI scanner, and they got what's considered the first clinically useful image. In August 1980, they used their scanner to identify a tumor in a patient. And they also found some other abnormalities. So that was a really big moment. It showed that MRI could actually be used to diagnose real medical problems.
Yeah.
It's interesting how all of this was happening, like all over the world.
Totally.
Different groups, different companies, all working towards the same goal.
Yeah. A really amazing example of international scientific collaboration. And, the innovations continued.
Right. So let's talk about some of the later advancements in MRI. For example, contrast agents. How did those come about?
Yeah, contrast agents, they've really made a big difference in what we can see with MRI. One of the first ones was gadolinium DTPA.
Yeah.
And the patent for that was filed in 1983. These agents, basically what they do is they change the magnetic properties of tissues just a little bit, temporarily.
Okay.
And that makes those tissues show brighter or darker on the image. So it can help you distinguish between different types of tissue, or it can help you see abnormalities that you wouldn't be able to see otherwise.
I see. So it's kind of like turning up the volume on certain things in the image.
Yeah, exactly. A good analogy.
And the scanners themselves, they've also gotten way more powerful over the years. We hear about things like Tesla. What does that even mean?
Right. So Tesla is the unit for measuring the strength of a magnetic field. Named after Nikola Tesla, of course, the famous inventor. Early MRI machines were something like 0.35 to 1.5 Tesla.
Mm-hmm.
But now, 1.5 and 3 Tesla scanners, those are super common in hospitals. And they give you much higher resolution images and they can scan faster.
Got it.
And research is still pushing the limits, too. There are these ultra-high field systems that go up to 7 Tesla, 9.4, even 10.5, and 11.7 Tesla. I mean, just to give you some context, your average refrigerator magnet, it's about 0.05 to 0.1 Tesla. So these research scanners, they are ridiculously powerful.
That's amazing. So not just stronger magnets, but also new types of MRI techniques, right?
Yeah, totally. So, for example, MR angiography, or MRA. It lets us see blood vessels in amazing detail without having to do anything invasive like traditional angiography. That came about around 1986. And then you've got diffusion MRI, DMRI, which measures how water molecules move around in tissues. It gives you information about the structure of tissues and is really important for studying things like stroke and multiple sclerosis. That was also developed in the mid-'80s. And then a couple of years after that, perfusion MRI was developed. And that usually involves using contrast agents to see blood flow, and it helps you tell the difference between healthy and diseased tissue, especially in tumors.
Wow, so many different ways to use MRI. And then there's fMRI, functional MRI. This one is mind-blowing. It lets us see the brain in action, right?
Absolutely. So fMRI, that was developed in 1990 by Seiji Ogawa. And what it does is it detects tiny changes in blood oxygen levels in the brain. So basically, when a part of the brain is active, it needs more oxygen, and fMRI can pick that up. And, the NSF, the National Science Foundation, they've funded a ton of research using fMRI. And we've learned so much about the brain because of it, like how memory works, how language works, how emotions work, and even, what goes wrong in diseases like Alzheimer's and dementia.
I see. And didn't DMRI lead to some other, even more specialized techniques like DTI?
Yeah, exactly. Diffusion tensor imaging, or DTI. and the related technique, tractography. They were both developed in the early 90s. They take the ideas from MRI and use them to visualize the white matter tracts in the brain.
White matter tracts.
Yeah, it's like the wiring of the brain, the connections between different parts of the brain.
Oh, okay.
In DTI, it's been really important for understanding brain development, neurological disorders, how the brain is affected by injuries, things like that. And then we've got, FELAIR, which stands for Fluid Attenuated Inversion Recovery. It was developed around 1992. And it basically helps you see lesions and abnormalities in the brain more clearly by suppressing the signal from the fluid around the brain.
Ah, interesting.
Yeah. And in the same year, arterial spin labeling was developed. And that's another way to measure blood flow in the brain, but it doesn't require any contrast agents. It's totally non-invasive. And then towards the end of the 90s, susceptibility-weighted imaging came along. That technique is really good at showing things like blood products, iron deposits, calcifications, because it's really sensitive to the magnetic properties of different tissues.
It's amazing how, every few years, there's some new MRI technique being developed.
Yeah, it's really incredible. And I mentioned MR spectroscopy, or MRSI, before. And that technique combines the spatial information from MRI with the chemical analysis you get from NMR spectroscopy. So you can not only see the tissues, but you can also identify and measure different chemicals within those tissues.
Chemicals like what?
Like metabolites. So these are small molecules that are involved in the body's chemical processes. And MRSI, it can help us understand what's going on at a chemical level in things like tumors, metabolic disorders, neurodegenerative diseases.
Got it.
And, more recently, we've also had the development of compressed sensing, which is really cool because it uses fancy algorithms to reconstruct images from a lot less data. So you can do scans much faster, and it makes things a lot more comfortable for the patient. Oh, and another big one. In 2020, the FDA approved this portable MRI system from a company called Hyperfine Research.
Oh, yeah, I've heard about that.
Yeah, it's a lower cost, lower power system that you can actually use at the bedside.
Yeah.
So it has the potential to make MRI much more accessible, especially in places that don't have huge, expensive MRI machines.
That's fantastic.
It is. And, throughout this whole journey, one of the best things about MRI is that it's really safe.
Right.
It uses magnets and radio waves, not radiation.
Right.
So it's not like getting an X-ray or a CT scan. It's really good for situations where you need to do repeated scans, like if you're monitoring a disease or seeing how well a treatment is working.
I see. And today, MRI is used for just about everything, isn't it?
Yeah, pretty much. Mammography, cardiology, sports injuries, neurology, you name it. It's used for detecting cancer, seeing if organs are working properly, looking at tissue injuries. I mean, really, it touches just about every area of medicine.
One thing that really jumped out at me from some of the articles you sent, especially the ones from PubMed and Science Direct, was the connection between MRI and our understanding of memory. How have those two things evolved together?
Yeah, it's a great example of how technology can push science forward in unexpected ways. Early MRI studies of memory, they were pretty basic. They would just measure the volume of different brain regions that are known to be involved in memory, like the hippocampus. But as MRI got more sophisticated, with things like fMRI and DTI, we could start to look at those brain regions in much more detail. We could see how healthy they were and how they were actually functioning.
Right. So not just anatomy, but actual function.
Exactly. And now, we can use DTI to look at the connections between those memory centers in the brain. And we can use fMRI to see which parts of the brain are active when someone is, trying to remember something. And this has been so helpful for tracking the progression of diseases that affect memory, and even for trying to predict who might be at risk for developing those diseases later on.
So MRI has given us this amazing tool for studying the brain, the mind, memory.
Totally. And I think it's worth remembering that at the heart of all of this is some really fundamental math and physics, like the Fourier transform. Remember I mentioned that before?
Yeah.
So that was developed back in the late 1700s, early 1800s by Jean-Baptiste Fourier, a French mathematician. It's a pretty abstract mathematical concept, but it turns out to be super important for how we process the signals in MRI and create those images. And of course, we have to acknowledge Bloch and Purcell again, the guys who discovered magnetic resonance in the first place. Without them, we wouldn't have any of this.
Right, right. So as we wrap up here, it's clear that the story of MRI is a story of incredible scientific progress.
Yeah, absolutely. Decades of research, people collaborating all over the world, this amazing drive to understand the human body. It really shows what we can achieve when we put our minds to it.
It's pretty inspiring. So to our listener out there, I want to leave you with this thought. What's next? What's the next big breakthrough in medical imaging? Will it be something that builds on MRI? Or will it be something completely new? Maybe AI will play a bigger role, or maybe we'll have even stronger magnets, or maybe there's some completely different way to see inside the body that we haven't even thought of yet. I mean, it's pretty exciting to think about.
Yeah, the possibilities are endless, really.
That's the beauty of science, I guess.
It is. There's always more to discover.